Welcome to our exploration of the quantum harmonic oscillator. I will take you on a journey from classical physics into the quantum realm. We'll start with familiar concepts like springs and vibrations, then discover how quantum mechanics revolutionizes our understanding of these systems. The quantum harmonic oscillator is not just an academic exercise. It's the key to understanding molecular vibrations, quantum field theory, and many cutting-edge technologies. By the end of this presentation, you'll appreciate why this seemingly simple system is considered one of the most important models in all of physics. The quantum harmonic oscillator is one of the most important and widely applicable models in all of physics. It's not just an abstract mathematical concept. It literally describes how atoms vibrate in molecules, how electrons behave in quantum wells, and how photons interact in laser cavities. This model is so fundamental that understanding it opens doors to comprehending everything from why molecules have specific shapes to how quantum computers might work. Today we'll explore this fascinating concept step by step, building intuition without getting lost in complex mathematics. We will try to understand the classical harmonic oscillator using the familiar mass spring system. Emphasize that in classical physics, everything is continuous. The mass can be at any position, move at any speed, and possess any energy value. This continuous nature will contrast sharply with the quantum version we'll explore later. The energy constantly transforms between kinetic and potential forms as the mass oscillates. The crucial transition from classical to quantum physics emphasized that at microscopic scales, the familiar continuous nature of energy breaks down into discrete packets. The wave-particle duality concept is central. Particles aren't just tiny balls, but have wave properties too. Most importantly, quantum mechanics is inherently probabilistic, meaning we can only predict the likelihood of outcomes, not exact results. This fundamental shift in thinking is what makes quantum mechanics so counterintuitive yet powerful. One of the most important concepts in quantum mechanics is energy quantization. Unlike classical physics where energy can have any value, quantum systems are restricted to specific energy levels, like steps on a staircase. The ground state having non-zero energy is a uniquely quantum phenomenon due to the uncertainty principle. The increasing gap between higher energy levels is another key difference from classical harmonic oscillators, where energy levels would be evenly spaced. As we know wave functions as the mathematical descriptions of quantum states. Think of wave functions as quantum fingerprints. Each energy level has its own unique shape. The ground state is like a gentle hill, smooth and simple. But as we go to higher energy levels, the wave functions become more complex, developing nodes where they cross zero. These shapes tell us about the quantum behavior and help predict where we might find the oscillator. The chart shows how these patterns evolve from simple to complex as energy increases. Unlike classical systems where we can predict exact positions and velocities, quantum mechanics only gives us probabilities. The probability distribution tells us where we're most likely to find the particle if we measure it. In the ground state, there's a single peak at the center, meaning the particle is most likely found there. But in excited states, we see multiple peaks and valleys, indicating the particle has higher probabilities of being found at specific locations while being unlikely to be found at others. The quantum harmonic oscillator isn't just theoretical. It has profound real-world applications. In molecular vibrations, atoms behave like masses connected by springs, creating characteristic infrared signatures that help us identify chemicals. Nanotechnology leverages quantum oscillators as incredibly sensitive sensors that can detect minute forces and displacements. Perhaps most fundamentally, quantum field theory uses harmonic oscillators to describe how particles are created and destroyed, forming the foundation of our modern understanding of physics and the universe itself. Let us summarize the key concepts we've explored throughout the presentation. The quantum harmonic oscillator fundamentally changes how we understand physics by introducing probability and quantized energy levels instead of classical certainty. It's not just an abstract concept. This model explains everything from molecular vibrations to quantum field theory. The combination of stepwise energy levels and wave-like probability distributions makes this one of the most important models in modern physics, with applications spanning from nanotechnology to our understanding of the universe itself. Role of quantum harmonic oscillators in modern research and future applications. Quantum oscillators are fundamental to quantum computers and sensors, representing some of today's most promising technologies. The concept continues to provide crucial insights that may lead to breakthrough materials and revolutionary technological advances. As one of physics' most elegant and powerful theoretical frameworks, the quantum harmonic oscillator remains essential for understanding quantum mechanics and will likely continue driving scientific discovery for years to come.